Good afternoon, everyone. Welcome all of you for today's live session. The live session for week 5 of Power System Engineering NPTEL course. And this will be the agenda for the today's live session, same as what we have been following in the previous weeks as well. So we will start with the brief overview of week 5 and then we will discuss certain problems related to the week 5. Just to remind you, the deadline for assignment 5 is February 28th, so please submit the assignment before, well within the deadline. And the recordings, the links for all the live session recordings as well as the presentation used for the session is available on the problem solving session tab on the portal. So you can download the PDFs for each week live session as well as the link for the YouTube link for the recording sessions you can get from that Google Drive link available on the portal. Let us start with the overview of week 5. So in the week 5, it was a continuation of the topic which was discussed in the week 4. So it was continuation of the corona, and then sag and tension was also discussed. Mostly the derivation part was involved here. So derivation for sag and tension. This we will take up in the next session. Today the problems will be focused on corona only, and corona was discussed in great details in this week 5 overview, in this week 5 material. So this should be week 5. I'll change this. Yeah, so let us, we discussed in the previous session also that the corona is accompanied by power loss, and then there is a luminant violet glow. There is, and which is brighter over rough and dirty surfaces as well as at the sharp corners or edges. And then there is a hissing noise or crackling sound, which you can hear even during the daytimes. And in if you stand below these high voltage lines, then this ozone gas is also released, which has its characteristic odor. And then this luminous glow you can observe maybe in night time. Sometimes you might have, especially during the rough weather conditions, you can observe such phenomena at night. So we will just go through this corona part now. The derivation was done in the lecture. So it is similar to the capacitance derivation, where the potential gradient GA comes out to be, for phase A comes out to be voltage for phase A to neutral voltage divided by R ln D by R. Similarly for the other phases as well. So from here we can say VAN comes out to be GA into R ln D by R. Similarly for the P phase as well as the C phase. So from here we Then finally we came at this for single phase and three phase lines. We calculated differently. Am I audible? Hello? Hello? Yeah. Hello? Hello? Am I audible? I hope I am audible. Yes. Yeah. So let us begin. So I was saying, so we discussed two important concepts regarding corona. So one was the disruptive critical voltage, disruptive, dis- and one was the visual. So this is the voltage. This is the minimum voltage at which the ionization of air around the conductor occurs and corona starts subsequently. And the potential gradient corresponding to this value, this voltage value is called disruptive critical voltage gradient. And this visual critical voltage is the minimum voltage at which the that visual glow appears. So this will be certainly higher than the disruptive critical voltage. So after that we discuss. So in entire Corona chapter there are four formulas that you have to remember. The four important formula. So entire discussion was based upon that. One was for disruptive critical voltage, then for visual critical voltage, and then two formulas for corona loss, total corona loss. And based upon these, you can solve all the numericals. So in case of disruptive critical voltage, so V naught RMS comes is equals to it is equals to G naught M naught delta into R ln d by R. So now here one thing which is important to remember is this will be in voltage per phase if everything is in meter. Okay, and the same will be RMS G naught M naught delta R ln d by R kV per phase if everything is in centimeter. So G naught also has to be in meter. So G naught will be 3 into 10 to the power 6 divided by root 2. Here G naught will be 30 by root 2 kV RMS per centimeter. This is voltage RMS per meter. Sorry. So if we remove these two terms, then it is simply G naught R ln d pi r. Okay. So this is considering that the surface is smooth as well as fair weather condition. To, let me add one paper. Sorry, one page. Yes. So when conductor surface is rough and dirty, then critical disruptive voltage will be lower. And critical disruptive voltage is less, and this is accounted by this M naught, which is called as the irregularity factor or the roughness factor. Okay. And this M naught is equals to 1 for smooth surface, smooth polished conductors. It is between 0.93 to 0.98 for rough and weathered condition. Rough and weathered, so old conductors. And 0.8 to 0.87 for stranded conductors. And this delta is because of the, let's see the air density factor, and which depends upon both the pressure and the temperature. Delta. This is 0.392 B to 0.273 plus T, where T is in temperature in degrees Celsius, B is barometric pressure in mm of Hg. Okay. So then the visual critical voltage. So this is the irregularity factor and this is air density factor. So both tend to reduce the both the critical voltage disruptive as well as the visual. The visual luminous glow of corona generally occurs at a higher voltage than the disruptive critical voltage. And why this voltage is higher, visual disruptive voltage. The maximum voltage of the maximum value of voltage gradient is G naught, right, which is 30 kV kV peak per centimeter. But this, as we have seen in we have seen that the voltage gradient reduces as we move away from the conductor. It is maximum at the conductor surface and it is lesser here. So ionization of air will occur away from this conductor. So the air is around the conductor. So when the voltage gradient will cause ionization when this value is reached at a distance of r plus 0.0301 root r. So this is another factor which here r is in, this is to be remembered, here r is in meter. And reason is that some energy required by the charged ions to start corona. So if maximum voltage gradient at the surface is 30 kV per centimeter, the value of maximum voltage gradient at any other point away from the center would be less than this, and thus there will be corona discharge at that point. So expression of visual critical voltage for a single phase line comes out to be 3 into 10 to the power 6 divided by root 2. This is 6 for single phase. Then MVR delta, this is V for visual, and this is 1 plus 0.0301 divided by root R delta ln d by r, where everything is in meter. This will give you voltage per phase. And for three phase line, this is for single phase. For three phase, it will be 3 into 10 to the power 6 by root 2 MVR delta 1 plus 0.0301 root R delta ln d by r. And here it is will be DEQ, because we have three phases, we have to find the GMR. So M is 1 for smooth conductor, so MV 1 for smooth conductor, so it is 0.7 to 0.75 for local corona. And for corona in general, which happens across the conductor length, it is 0.8 to 0.85. So for a corona happening across the length of the conductor. So this is done. And this we already discussed that the value of the maximum voltage gradient G naught, it depends upon the air density of the air, because the dielectric strength of air is proportional to its density over a wide range, and thus it is directly proportional to barometric pressure and inversely proportional to temperature, and that is why we have this formula 0.392 B divided by 273 plus T. So here we have to remember that B is in mm of Hg mercury and T is in degrees Celsius. Then we discuss the corona power loss, which is due to the corona discharges. and for their estimation is done using some empirical formula based upon the different kind of experimentations and observations carried out by different people. And two different formulas are very popular. One is the Peake's formula, and another one is the Pterson's formula, and both are used for different. They give accurate answer for different values. So we will see that the Peake's formula, this one, is equals to 244 by delta air density factor into f plus 25. F is frequency here, and into root r by d. D is separation. Let me write it as capital D. R is the radius of the conductor. Then it is V phase voltage. Then disruptive critical voltage V0 into 10 to the power minus 5 kilowatt per kilometer per phase. So if you multiply it by length of the line, then it will be kilowatt per phase. If you multiply it by 3, it will be total corona power loss. So always remember, this is frequency, supply frequency, this is conductor spacing. If it is if they are placed on the corners of equilateral triangle, then the same D equation. Then R is the radius of the conductor. This is phase voltage, critical disruptive voltage to neutral. Delta is air density factor. For single phase line, Vn is 1 by. So this is to be remembered that for a single phase line, Vn is 1 by 2 times the line voltage, and for 3 phase Vn is VL by root 3. So Peake's formula for corona loss is valid. Let me call it as, we'll call it as P corona loss K peak, and this we call it as Pterson PT. PT for Pterson, PK for peak. So PKC is valid when the ratio Vn by V naught or Vd naught, we have written it as Vd naught. So this is Vd naught, it is greater than 1.8. So, and if the ratio is less, then the Pterson formula is more accurate when Vn by Vd naught is less than 1.8. So we will see that also. What is the formula? For that, we will need a table, but the value will be provided in the question for Pterson's formula. So Pterson's formula PTC is equals to 2.1 half into Vn by log d by r whole square into 10 to the power minus 5 f kilowatt per phase per kilometer. So this f is the ratio Vn by Vd naught. Other values are here. Vn is the RMS voltage in phase to neutral, phase voltage in kV. Same, everything is same. Now because we have seen that critical disruptive voltage, let us write it again here as G naught, which is 0.392 b upon 273 plus t delta g naught delta m naught r ln dy r. Okay, now it depends upon so many things. It depends upon voltage gradient, depends upon pressure, temperature. Radius of the conductor, then conductor spacing. Sorry. So now let us see what is the effect. And so this is VD naught, okay. And PC we have from Peake's formula. Let me copy this. 244 by delta F plus 25 root R by D V phase minus VD naught square into 10 to the power minus 5 kilowatt per kilometer per phase. Yes. So if the difference between the V phase and VD naught increases, then the corona power loss increases. So first we'll see what happens with the effect. This is effect on corona power loss due to the change in system voltage. So effect of system voltage. What happens with the change in system voltage? So we all know that the electric field intensity in the space around the conductor is dependent upon the potential difference between the conductors. And if potential difference is high, the electric field intensity is going to be very high, and hence the corona loss will increase because this difference will increase. Suppose VD net is constant and V phase is increasing. So what will happen? The difference will increase, and hence the power loss is also going to be increased. So with the increase in system phase voltage, the power loss increases as V phase minus VD naught square increases with other parameters remaining constant. Now, what will happen with frequency? That we can easily see. The PC is proportional to F plus 25. So if frequency increases, the corona loss will increase. So F increases, PC also increases. Then effect of density of air. So because density depends, we can see here, it depends. Density will affect this which disruptive critical voltage, and which is dependent upon pressure as well as the temperature. So coronal loss is inversely proportional to the, and here you can see coronal loss is inversely proportional to this. Yes, so this is inversely proportional to delta. Okay, so if the coronal loss increases with decrease in density, so because coronal loss is inversely proportional to delta, So if air density reduces, then corona power loss increases. And how this delta can decrease? For that, either B has to decrease or temperature has to increase. The pressure decrease or temperature increase. The pressure decrease will. So that is because pressure is lower at higher altitudes. That is why we will see the air density at that higher altitude is lower. So corona loss is higher. That is why the corona loss of a high voltage line passing through a hilly area may be higher than that of similar transmission line plane due to lower value of delta at high volt. So PC is higher for transmission lines at higher altitudes. In plain areas. So let me remove this because I want to keep this. Let me copy this. I will insert one more page and I will copy it here. Yeah, so now we'll move to the radius part, fourth one, effect of conductor radius. So if conductor radius is high, what will happen? The surface field intensity is less because area is more. We have seen that at sharp edges, the intensity is high. So if radius is high or large, then the field intensity is lower, and as a result, sorry, the corona loss is also lesser. So that is why for different types of conductor, corona losses will be different. For same current capacity, the ACSR conductor has larger radius than single copper conductor because it is stranded. Therefore, transmission line of so corona loss for ACSR transmission line is less than corona loss for single copper conductor transmission line. And for bundle conductors, also it is less because the effective radius is larger. So if this is a single conductor, then in bundled conductor we can have like this configuration. So there will be a bundle of 3 conductors, or we can have a bundle of 2 conductors, or we can have a bundle of 4 conductors. You would have seen this. Practically you can see. There can also be a bundle of 6 conductors. I haven't seen 6 one, but 2 are very common to be seen. These are bundle conductors. So their effective radius is more than the single conductor. So if radius is more, then corona loss will reduce. Effect of temperature rise of conductor by load, because we have seen that PC is inversely proportional to delta, and delta is also inversely proportional to temperature. So PC will be directly proportional to temperature. To current conductor current raises the current temperature, conductor temperature, and hence leading to an indirect reduction in corona loss. So conduct corona loss is larger if the current temperature is low. For lower temperature, corona loss is larger, and this is due to the fact that low temperature dew drops collect on conductor surface during fog and humid weather. High conductor current prevents such condensation and reduces corona loss. Effect of snow and forced frost. So the effect of snow and frost is that they cause very high corona loss and radio interference. So let me erase this. So conduct we have seen for lower temperature corona loss is higher, and for snow, effect of snow and frost is that it also leads to high corona loss and radio interference. Yes, the next is new and old conductors. So on new conductors, corona loss is more due to scratches and burns, etc. On old conductors, it decreases because effect of dust. So dust and dirt. So we have already seen corona loss is more here. Conductor configuration. Corona loss under foul weather condition is also very higher as compared to the fair weather condition. So corona loss, foul weather is more than corona loss in fair weather condition. Then conductor horizontal or vertical. So horizontal and vertical, therefore this. So if they are placed in horizontal or vertical fashion like this, vertical, this is horizontal or vertical, then the electric field intensity at the surface of middle conductor is higher. So if electric field intensity is higher, then more corona loss in the middle conductor. But if they are placed in equilateral fashion, then it will be same throughout. So all the conductors have equal field distribution. The corona will be less if they are placed in equilateral fashion. So you will find equilateral fashion is more widely used. Then we moved on to numericals. Now, so before moving to the numericals for this, we will see some introduction to sag also, sag and tension. So sag and tension analysis is very important for distribution and transmission line, and especially for the transmission line, especially in the vertical configuration. If the conductors, all three conductors are placed in vertical fashion between two towers, let's say this is the one tower, tower 1, and this is the second tower separated by a distance L. This is the second tower. Then this sag has to be uniform in all the three conductors. Otherwise, there can be problem. If this comes closer to the A phase, come closer to the B phase. So this will be called as the sag. And how much should it be? So this has to be carried out, and there are two. One is catenary curve method. Another is as using parabola curve. This one is an approximation. So if the distance between two towers is quite large as compared to this sag, then this can be used. This approximation is good. Otherwise, catenary curve method has to be used. We will see the formula in the next time, but today we'll just see uh, why it is so important. So before the erection of the transmission line, sag needs to be calculated. The amount of sag and tension to be given to the conductor at a given temperature. So what needs to be done? Amount of sag and tension to be given to the conductor at a given temperature, maximum wind speed, and possible ice loading. It is considered that the force due to wind will be, if wind blows, if conductor is going like this and wind blows, if weight of conductor is like this, so velocity of wind is right at right angles to the weight of the conductor, and this will cause a major deviation movement in the conductor, and if these conductors are placed horizontally, then that can create problem. So it is, the lines are designed for the maximum wind speed that will happen when the wind speed is perpendicular to the weight of the conductor. All these things are needed in order to specify tension to be used in stringing the line conductors. So value of sag and tension in summer and winter must be known. The main factor for in the design and stringing of conductors on the support are, so one is the conductor load per unit. Conductor load per unit length. So weight of the conductor per unit length. Then conductor tension. It especially becomes important for dead end transmission lines and interchange. Then span, that is, this is span. Distance between the support. Then temperature. And for determining this load, what are the factor needs to be considered? That is weight. That's why it is called load here, not weight. Weight of the conductor, because it will include weight of the conductor plus the effective weight because of the wind speed, and then ice loading. The ice loading will further increase the load on the conductor. Effective weight will increase. So wind actual weight plus wind plus ice. All these will lead to the effective weight or load on the conductor. Then the next was the derivation of the conductors that will not go through. Now we will let us see the numericals for week 5. Yeah, this is the first one. First question for week 5. The first question is the effect of corona is reduced by. So we know that corona loss is 244 by delta 25 square.
Discount. Where was the present?
If the radius increases, so class, online classes. If the radius of the conductor increases, then the field intensity will reduce and the corona loss will also increase. Sorry, reduce. And what will happen if the spacing between the conductor increases? Then also corona loss will be reduced. Because we can see here It is indirectly proportional. So that is why it is. That's why we saw that bundled using ACSR conductors as well as bundled conductors. We are increasing the effective radius of the conductor. So R effective. And by increasing the D also, we are reducing the Corona loss. Which is reduced. Because we can see this VD naught is proportional to D. That's its LND. So if we increase the, then VD naught will also increase. That is means higher value of, so corona will start occurring at a higher voltage. The voltage required will be very high. So that means we can reduce corona loss. And also here it is inversely proportional to capital D. But the increasing the conductor size as well as the conductor spacing, corona loss reduces. This is very important. So corona loss will reduce for increasing the conductor size as well as the spacing. Then this also we have seen what will be the effect of dirt. So whenever there is a rough and dirty surface, the VD naught reduces, the critical disruptive critical voltage reduces. Then the difference between V phase minus VD naught increases and the power corona loss also increases. Is 2. So this increases the irregularity and thereby decrease the breakdown voltage. So corona will now start occurring at a lower voltage. So dirt when rough surface. So this is given by the irregularity factor MV and M naught. So here we are concerned about M naught. So surface irregularity factor or the roughness factor. So if this increases, then the irregularity the increases and the breakdown voltage reduces. Correct. So what will happen in the humid weather? This also we have seen corona loss for foul weather condition is much larger than, no, never equal to fair weather condition. So corona loss. Okay. So this is corona loss. So what will happen? In humid weather, the corona occurs at a voltage lower than that needed in the fair weather. So VD naught foul weather is less than VD naught fair weather. Now we will move on to the numericals. So let us start with the first one. The first one is the breakdown strength of air at STP. It is given as breakdown strength is given as G at STP naught, we can say 3 kV peak per mm. 30 kV peak per centimeter. 3 into 10 power 6 voltage peak per, sorry, yes, peak. Because this is 30, 10 is power 3 voltage peak per centimeter. So it will be 3 into 10 is power 4 divided P peak divided by 10 to 1 is 2 meter. So this becomes T into 10 is power 6 voltage peak per meter and 3 into 10 is power 6 by root 2 VRMS per meter. So in centimeter it is 30. And this is in centimeter. 3 into 10 is power 4. Now 30 kV peak per centimeter and 30 by root 2 kV RMS per centimeter, which is around 21.1 kV RMS per centimeter. So here what is given, G naught is given, and the breakdown strength of air in kV RMS per centimeter at 20 degrees centigrade, 27 degree and 75 centimeter wedges need to be calculated. So we know that G dash is G naught into delta air density factor, which cell intense in turn depends on 0.32 B by 273 plus T. So here it is in mm of Hg, 750 divided by 273 plus temperature 27. How much is this? Let us calculate. How much is this? 0.392 multiplied by 750 divided by 273 plus 27. This comes out to be 0.98. So G dash is G naught into 0.98, which is the required answer is in kV RMS per centimeter. So it is 30 into 0.98 divided by root 2. 20.78. 20.78. 8 or 7. 20.789. 20.8 kV RMS per centimeter. This is G dash. So let us check whether it's correct. It's correct. 789 kV RMS per centimeter. So this you have to remember, this B has to be in mm of Hg, and in peak per meter it is 3 into 10 power 6. When this is 30 kV per, yes, this, so then it is in voltage per centimeter, that to peak value. For RMS value divided by root 2. Okay, next. So this is the next question. The breakdown strength of air at STP. This is done. Now the next question is this. Equilaterally spaced three-phase AC transmission line. Total corona loss 35 kilowatt at 220 kV line to line. So this is always V line to line and 45 hertz. Peaks formula. It's a very easy question. If supply frequency is changed to 50 Hz, 55, keeping all other parameters unchanged. If everything else is same, then it becomes k times. Hmm? But we don't know k. So what we can do? Take a what we call it? Divide the two. So PC at 55 Hz divided by loss at 45 Hz is equals to 80 by 70. This implies power loss at corona power loss at 55 Hz is 80 by 70 into 35. This is 40 kilowatt. Okay. Yes. Is this fine? Such type of questions are very easy. You just have to see what is given and what needs to be calculated. So carefully read the question and mark out things which are given and what needs to be found out. Now let us move to the next question. So this is the answer. Next question is this. So fifth question, I think. So 130 to 50 hertz, three-phase transmission line, right? Maybe 50 hertz, three-phase, 2.4 centimeter diameter conductor. This implies the radius is equals to 1.2 centimeter. This will show that corona takes place if voltage exceeds So VD naught is given as the disruptive critical voltage. (230 kV RMS). If the line voltage exceeds this, critical disruptive voltage to neutral will be 230 kV RMS by root 3. If the value of potential gradient at STP at which ionization occurs, so it is given G naught as 30 kV peak per centimeter, so it will be 30 by root 2 kV RMS per centimeter. Then what is given? M naught irregularity factor is 0.94, air density factor is 0.98, assuming that conductors are placed in an equilateral triangle and the line is regularly transposed. Sorry. So transposition is so what do we need to find out here? This find the spacing in meter between the conductors. So if everything is in meter, this is in RMS per centimeter. In meter, it will be 3 into 10 power 6. We know, right? So VD naught is 3 into 10 power 6, where everything is in meter. Then T naught, delta, M naught, R in meters, and D in meters, and R in also in meter, DEQ. This is voltage per phase. This is given as 230 by root 2 into 10 power 3. We have to find out DEQ. So, yeah, let me insert one blank page. Yeah, so let me copy this one. Yes. Yeah, I have raised. Yeah. So yes, this will be 10 power 3. So 3 into 10 power 3 into delta was how much? 0.98. M naught is 0.94. R in meters. R is 1.2 into 10 to the power minus 2. Because that was in centimeters. Ln d by r. D we need to find out. R is 1.2 into 10 to the power minus 2 is equals to 230. Now let us try to calculate this. How much is this? 30 divided by 3 divided by 10 to the power 3 divided by 0.98 divided by 0.94 divided by 1.2 divided by 10 to the power minus 2. So this I am getting as ln d by 1.2 into 10 to the minus 2 comes out to be 6.9354. So d will be 1.2 times to the minus 2 e raised to power 6.9354. Some error is there. Let me check this again. What was the value? Maybe some calculation mistakes. So 30 kb by root 2 is correct. M naught is 0.94, 0.98. So it is 3 into 10 is power 3 into 0.98 into 0.94. Yes, this is the mistake. Sorry for this. This should be root 3 phase voltage. This should be root 3. So it will be root 3. Yes, now D comes out to be 3.455 meters. So this is correct. So this you have to keep this in mind. So we had to take this voltage which was given was line to line. So the voltage, this is line to line, but we want phase voltage. So this should be root 3, not root 2. This was a mistake that I was making. So you don't make such mistakes. Be careful. Yeah, let us move to the next one. Next is let us write everything. That 132 kV. And this is done 3.5. So three phase 220 kV 50 Hertz frequency 100 kilometer length of transmission line consists of 20 mm, मतलब 2 centimeter diameter. So radius is 1 centimeter or 10 is for 2 meter. Conductor space at D is equals to 3.5 meter at the corners of an equilateral triangle. Calculate the disruptive critical voltage between lines. So temperature is given 24 degrees centigrade. Barometric pressure is also given mm of Hg. Surface irregularity factor m naught is given as 0.95 and G naught 21.1 kV RMS per centimeter. Or we know that this is 2.1 10 power 6 volt per meter VRMS. So we know that VD naught is G naught M delta M naught R L D by R volt per phase. This is per meter. So G naught is 2.1 M naught is 0.95 delta. You have to calculate here. First, let us calculate delta. 1392 B 273 plus T. Substitute all the values. B is 740. Temperature is 24. So how much is this? Point 9767. R 10 is power minus 2 ln. D, how much is D? 3.5. So calculate this. So this is voltage, disruptive critical voltage to neutral. We have to calculate it between lines. So it will be root 3 VD naught. R, why did I take 1 point, what did I do? Okay. Yes, almost you will get everything. Due to this 21.1, it is coming different. Plus 3 divided by is 2.12. So that is why. So you can check that. Now let us move to the next question. So the next question is three phase 220 kV 50 hertz 1 kilometer long transmission line consists of 1.6 diameter conductors. So radius is zero point 0.8 into 10⁻² meters. Calculate visual critical voltage to neutral. Assume temperature as 22 degrees Celsius. Barometric pressure as 735 mm of Hg. Surface irregularity factor is 0.92 and G naught is 21.1 kV RMS per centimeter. Yeah. So V visual is equals to G naught delta MV MV, and here we know that it is a factor of 0.301 R delta into R ln d by R. Here everything is in centimeter. G naught is also in centimeter, which is already 21.1. So if I write it as 21.1, final output will be, this will be kV per phase. 21.1 into delta is how much? Here is delta again. So I always forgot to calculate delta. It's 0.392 B is 735 273 plus 22. So it is 0.9767. So G naught is 21.1, 0.9767, and V is 0.92 plus 0.301. What is R here? R is 0.8 centimeter into delta 0.9767, 0.8 centimeter ln D in centimeters. How much is D? 3 meters, 300 centimeters divided by 100. So let us calculate how much is this. ln 300 divided by 0.8 multiplied by 1 plus 1301 divided by root of 0.8 767 multiplied by 0.92 multiplied by 0.9767. So it is coming as Why am I making some mistake always today? Let me calculate this again. 12 300 divided by 0.8. 5.92 multiplied by 0.8 multiplied by, let us calculate this first. Root of 0.8 multiplied by 9767 inverse multiplied by 0.301 plus 1 multiplied by 0.92 0.9767 multiplied by 0.8 multiplied by 21.1 multiplied by ln 300 by 0.8 120 point. Yeah, now it's correct. This I'm getting as 120.51 kVRMS per phase. Same thing here we have to calculate. So here, if we see what is the phase voltage here, 220 by root 3, which is how much? 220 divided by root 3 is, it's 127.02 kV RMS. And this is visual critical voltage. Because the intensity at the surface is highest, then it is reduced. It is less as we move away from the surface. And this here G naught is, let's say it is maximum. Let's say G naught. So at a distance 1 plus this R into 1 plus R plus this is less. Hmm? This happens at a lower voltage. Next, this is done. This was easy. Now, next two questions are on this corona power loss calculation. Using peak formula, let us write the peaks formula first. Okay, we'll write it later. Let us write what all things are given to us first. Um, One is given rough weather condition. Then 132 kV, 50 hertz, three phase, 175-kilometer long transmission line consists of 1.6 centimeter dia. So this is 0.8 centimeter. Standard copper conductor range in 3.5 meter delta. So D is 3.5, 350 centimeters. Barometric pressure is 750 mm of Hg. Temperature is 26 degrees centigrade. Irregularity factor 0.86 and G naught is 21.2 kV RMS per centimeter. Disruptive critical voltage under foul weather condition is 0.8 times fair weather condition. So let us calculate first the air density factor. How much is delta? 0.392 P upon 273 plus T. This comes out to be 750 273 plus I'm going to choose this 26. Point 9833. Now let us calculate VD naught. Let me copy this. Yes. So let us calculate VD naught. VD naught is G naught, which is given. M delta, both are. This is given, which we have calculated. R L N D by R. This is 21.2. Everything is in centimeters. This will give us as kilovolt. M, how much? 0.86. So this is for fair weather. Then delta is 0.9833. R is zero point 0.8 centimeters. Ln 350 by zero point 0.8. How much is this? 0.86. So I'm getting something like this. Please check the calculation once. So if you take it as 21.2, you will get this. And if you take it as 21.1, then it will get 28.6. This is for 21.2. This is for G naught is 21.1. So now fair weather is on. Foul weather VD naught is zero point 0.8 times VD naught. So 0.8 into 86.80. 0.8. This is 69.44 kV. So now I have to calculate the power loss. Corona power loss. Okay, let me copy this. And let's add a page. Yeah. So now let me remove certain things from here. What we already calculated, we don't need them. Yes. So we did not dash under foul weather. 69.44 kV. Corona power loss. Total Total current of that means three phase. This will be 3 into 244 by delta into F plus 25 into R by D V phase minus V naught V D naught dash here as kilowatt per kilometer. We need to multiply it by length also 175. So we'll do that at the last, or let us remove this also. We'll add this later. So 244 by delta. How much is delta? Where is delta? 0.9833. Frequency is 50 hertz. This becomes 75. R is zero point 0.8. This is 350. V phase was 132 by root 3. This is already in phase. Kilowatt per kilometer per phase. Per phase. So let us calculate how much is this. 244 multiplied by 75 divided by 0.9833 multiplied by root. Let me connect charger. Yes. 60. V phase is how much? Minus 69.44 square. So this will be 3 times multiplied by 175. One is phase, another one is length of the transmission line. This is going out to be no, this will go out to be around 214 point something. Okay, same thing. What is done here? So everything here is in centimeter. This is the last question. Let's do it. So this is given using Peake's formula determine. Um, yes, this Pterson's formula determine the total current loss in kilowatt for 220 kV, 50 hertz, 3 phase, 160 kilometer long TL, TEQ is 625 R. R is the radius of conductor in centimeter. Assume F is given. So we saw that when Vn by Vt naught is less than 1.8, we use the Peterson's formula. Let me copy that. If Peterson when this is less than 1.8, yes, this one is the formula. Okay, 2.1 into f frequency, Vn is how much? 220 by root 3 and log d. This is base 10. How much is Teq? It is 625 R divided by R into 10 to the power minus 5 into F is 0.08 kilowatt per phase per kilometer. Let us calculate this first. Divided by log 625 square multiply this is Peterson's formula and this is kilowatt per phase per kilometer. Now we want total current loss, so we want to multiply it with ETC total to 0.1733 multiplied by 3 for 3 phases, 160 for the length of the line. It comes out to be 8.1 kilowatt. Let us do one more numerical, right? Insert one more page. We will do one more numerical. Let us take this example. So we have, if the so this is based upon the concept that if the actual operating voltage is less than the then there is no corona loss. So if in any question you are asked to find out the corona loss and even the VD naught is not given, and you need to calculate that in that question VD naught, then you have to check after calculating this VD naught, is this VD naught less than or greater than the sorry uh, the operating voltage. If it is greater than the operating voltage, then there is no corona loss. If it is less than the operating voltage, then there will be corona loss, and then only, otherwise it will be zero. Even though we have the formula, but that formula is will give you loss only when V phase minus VD naught is positive. So if V phase is greater than, so operating voltage is greater than VD naught, then otherwise it will be zero. Otherwise, corona loss, you have to report the corona loss as 0 kilowatt, not the value which you have found out using the formula. So we will see this last question. Say 220 kV, 3 phase, 50 hertz, 200 kilometer long transmission line. Consists of three stranded aluminum condensers stranded triangularly spaced triangularly at, so D is 480 centimeters and radius is 1.5 centimeter. Air temperature is 27 degrees Celsius. B is 740 mm of Hg and breakdown strength of air is 21.1 kV RMS per centimeter. Surface factor 0.85. So disruptive critical voltage we have to find out. Let us find out VD naught. So for that, I always make this mistake. First of all, let us calculate delta, which is 0.392 B 273 plus T. So it is 0.392 and B is, where is B? 740, and this is 273 plus 27. So how much is this? So VD naught is M G naught M delta R ln T by R. G naught is 21.1 into M is 0.85, 0.967, R is 1.5 ln D, where is T for 480 by 1.5. So this comes out to be 150.06 kV per phase. So this is VD naught. Now operating voltage, how much is V phase? This is a 220 kV line. 220 kV divided by root 3. This is only 127.02 kV. So VD naught here is operating voltage is less than the disruptive critical voltage. So corona will never happen. We know that the disruptive critical voltage is the minimum voltage at which the corona begins. The ionization of the air around the conductor starts. So, but if the operating voltage is less than the critical disruptive voltage, this will never happen. So there will be no corona loss here. So it will be waste of time to, and it will be not just waste of time, but it is incorrect to use the formula, the Peake's formula here, and calculate the power loss. What you will see, VD naught divided by V phase, you will find out it to be 1.18. So Vn by Vd naught, V phase. 0.8. Sim- so we cannot use this. There is no corner loss. Okay. So we have calculated the. Let us calculate the visual this critical voltage. So MV, it is given local is 0.72 and MV general general. This is 0.8. So for this we know the formula, right? So V is G naught MV, for this is for local. This will be local. Delta 1 plus 0.301. So 0.0, if we're taking everything in centimeter, then R into delta into R ln D by R. So we have, let us calculate. G naught is 21, MV is 0.72, delta is 0.967, 1 plus 0.301, R is 1.5 into 0.967, 1.5 ln D. How much is D? D 450 by 1.5. This is 157.1. And then you'll find MV channel, then it will be more than that because it is 0.82 and it is 0.87. So we know that this also we can directly calculate. It is very easy. We know that sorry, we know that MV say or in general MV rightly, but sorry, the MV general that we call MV general is this and MV local is this and VV is proportional to MV. So VV general upon VV local is equals to MV general by MV local. This implies VV general is equals to VV local into MV general by MV local. So VV general how much? 150.7.82 by 0.72. This is 178. Okay. So we have covered all the questions for Corona today. The next time, what we are going to do is we will move on to the sag and tension. We will see important formulas, not without going into deep in the derivation and its importance. So we'll see its importance and important formulas, and then we will see some problems. I will show you some images also for different types of towers and sags between them. It's very interesting to know all these things, especially for power system engineer. Designing although this erection of transmission line requires civil mechanical as well as electrical component, but electrical part is a very important thing here. How much should be the sag is a mechanical thing at only. If we see, if there are two towers, one is height h1, h2. So if both are same, then sag will be in mid. It will be in middle. This will be L by 2. This is will be L by 2. But here in this case, if it is x, this is L minus x. Both are not same. So this is because of the height. So this also we need to consider. How much will be this x will depend upon the required tension as well as the weight as well as the difference between the height. So we will see this all these things next time. Thank you very much for attending today's session. We will meet next same time. Yeah, the time will be posted. So okay, thank